Hello everyone. I'm going to introduce OpenExpress, which is a fully hardware automated open research framework for future NVMe devices. My name is Myoungsoo. I'm the lead of Camel Lab and an associate professor of KAIST. This work has been performed as a part of an open interface project sponsored by Memray Corporation. So let me start with the discussions of emerging non-volatile memory trends in terms of, in particular, latency. This figure shows read latency behavior on y-axis, and I listed up the different memory technology at x-axis. I put the DRAM latencies as a baseline since emerging non-volatile memory performance get close to DRAM's ones. And TLC is the most popular flash technology and support 450 microseconds for reads. MLC offered smaller storage capacities, but its read latency is around 150 microseconds. Even though SLC is an old technology, it exhibits the fastest read latencies around 20 to 25 microseconds. Inspired by the SLC, the new flash, such as GNAND and XL Flash, shows 3 microseconds while offering high storage capacity with a 3D stacking mechanism. The PRAM uses a different storage core and offers DRAM-like performance behavior by changing the core state between amorphous and crystalline. MRAM offers even better performance than DRAM, as it is designed toward to replace SRAM. TLC, MLC, and SLCs are all flash technology, while PRAM and MRAM can be classified as storage class memory because of their fast access speed and byte addressability. These SCMs open a new opportunity to incarnate future NVMe storage subsystem. So before jumping into the design of the future NVMe storage system, let me introduce NVMe internal components and the interface detail. The modern SSDs employ an embedded CPU and multiple I/O buses called channel. Each channel contains a flash controller and multiple flash packages to improve storage level parallelism. These internal components are connected to the host over PCI Express. The host enables PCIe over NVMe protocol by employing storage stack that consists of file system, page cache, block layer, and the device driver. While conventional SSD having a thin storage interface such as SATA, they offer around 500 megabytes per second at usual level. The bandwidth of a high-performance NVMe SSD is around 1 to the 3 gigabytes per second, which is 2 to the 6 times higher than conventional devices. As the storage stack is designed for spinning disk, mostly, many researchers have been started to redesign the stack and/or to optimize both devices and the storage stack in a cross-layer optimization manner. The challenges behind the system and the storage research community are that all SSD vendors do not share their own hardware and software IPs, and it is exhibited to accesses from the public. This unfortunately makes the studies rely on simulation or kernel-level software emulation. The another challenge that we have to consider is the firmware execution overhead with the emerging SCMs. When one replaces flash with SCMs, the new storage card performance can bump up against the bandwidth capacity of PCIe interface and make it a CPU performance bottleneck. So let's go over what CPU needs to do for the NVMe storage card as a kind of background knowledge. The NVMe defined two different queues, submission queue and completion queue, on the host side memory as a logically paired I/O queue. The storage card also exposes a set of doorbell registers such that the host can let the embedded CPU know an update of submission queue and completion queue. So let me show what the embedded processor should do for NVMe communication. When a user submits I/O request to the submission queue, the NVMe commands include the physical region page, PRP, that indicate the actual data location of the host system memory. The host then writes the doorbell register to let the storage know the submission queue update, and the underlying processor requires detecting the doorbell ringing. Once it has been detected, the storage side processor fetches the issued command and parses the command into the storage level information. Then the processor decodes PRP and performs data transfer in an active manner from the host side to the storage side. And from transfer the data, the embedded processor processes the I/O request to the underlying storage media. Once it has been done, the storage side processors require issuing the compilation command to the compilation queue. To let the host know about the compilation queue update, it should signal an interrupt over a PCI path. The host interrupt service routine is then invoked and finish the request up. Lastly, the host interrupt service routine completes the services and inform it to the storage device by writing the doorbell register again, which is required to monitor the target doorbell register. So all this NVMe activity give a burden on the storage side processor. To address this burden, a modern NVMe SSD employ a multi-core or even many-core processor as their embedded CPU. The cores are sitting between PCI client logic and the back-end SCM controller. This front-end compute complex also contains internal memory controller and connect them all together over an interconnect network. So let's decompose the latency of the multi-core based NVMe SSD in order to figure out what makes us reconsider the current SSD architecture and design. The pure storage media latency in this figure highlighted by black, and in this analysis, x-axis lists up the different NVMe technology from the flash to the emerging storage class memories. The embedded CPU first requires to fetch the NVMe command from the host memory to the underlying storage side resources, which take a small portion of the latency breakdown of this analysis. It also needs to manage the queue and doorbell management. The processor performs data transfer by parsing the PRP. Note that this analysis is performed for the cases of a single PRP. So in a larger block processing and/or real workload execution, the portion of the PRP processing latency can be greater. Based on the type of the target storage media cores, it needs address translation between logical pages and the physical pages. Lastly, the processor is involved in handling I/O compilation, which include preparing the message interrupt signal, MSI packet, and an interrupt. As shown in the figure, the CPU burst can be overlapped with the I/O burst for flash memory cases. What does this mean by is the many-core or multi-core SSD is sufficient to hide firmware execution behind NAND I/O activity. However, since emerging SCM latency get close to DRAM performance, the firmware control can become the critical performance bottleneck. To address aforementioned two different challenges, we introduced OpenExpress, which is a framework that fully automates NVMe control logic in hardware to make it possible to build a customizable device. The OpenExpress doesn't require any software intervention to process concurrent read and write NVMe requests. It also supports scalable data submission, reach outstanding NVMe commands, and the submission compilation queue management. We prototype OpenExpress on a commercially available Xilinx FPGA board and optimize all the logic model to operate a high frequency. The OpenExpress removes the conventional multi-core front-end. To this end, we place a system-on-chip memory bus between PCI client and a back-end SCM channel complex. The OpenExpress consists of three groups of hardware models: queue dispatching, data transferring, and compilation handling. These three groups of hardware model operate in a pipeline manner and create read and write data path in a fully hardware automated manner. So let me show how the design detail look like. For doorbell registers, OpenExpress exposes a set of doorbells called region to the host. For NVMe command fetching and I/O parsing, OpenExpress allocates FAT, standing for SQ Entry Fetch Manager. To monitor an update of doorbell region, the fetch manager snoops the AXI bus that consists of address, data, acknowledge channel. The OpenExpress has HTRW, that stands for the hardware transfer for read and write model, and the backend DMA model composed by FPGA micro DMA IP cores. This will perform data transfer between PCIe endpoint and the backend memory channel models. The compilation handling logic is architected similar with the queue dispatching mechanism. It has a doorbell region for the compilation queue, and CMT, compilation handler, that manages interrupts and I/O compilation that relates to MSI and the queue entry release. As an implementation issue, we place two sets of doorbell regions together and call it as NVMe Context Manager. This CTX also contains a queue size, base address, max queue size, and etc., which is necessary to incarnate an NVMe SSD. So let me explain the operation flow of OpenExpress. At the first time, the user can issue a command by writing NVMe entry to the queue entries, and then write SQ tail pointers and then ring the doorbell register. OpenExpress monitors the doorbell region and the signal on event to underlying FAT. The FAT then fetches 16 double-word SQ entries from the host side memory, and it parses such I/O command to the storage level information like logical block address, sectors, and the operation code. And the FAT sends the parsed command to the underlying HTRW, which is the PRP engine. Now the PRP engines will go through the host system memory again, and then parse the PRP entry information. And once it figured out all the location of the data, then it copies the data associated with each PRP pointer to the underlying storage backend. Once OpenExpress has been done with the I/O processing, it posts the CQ entry to the host side. And OpenExpress also creates MSI packet and interrupt the host. So the host now knows the I/O compilation. So the host side device driver will invoke the interrupt service routines and then finish up the everything about the such issued I/O request. So once it has been done, the host write the CQ header pointer again with a doorbell register update. So the OpenExpress monitor it and then release SQ and CQ, which is a pair of the NVMe I/O queue. In the implementations, we use more than 100 primitive and IP cores, including the front end, CTX, CMT, HTRW, and the FAT. The front end here is a connection complex for the PCI interface and the ATC subsystem. Among the 100 IP cores, we can highlight and summarize the logic into 5 major IP cores aligned with OpenExpress's operation flow. These models require frequency tuning and optimization to reduce the loud delay and the negative slacks. So we connect all the hardware logic by minimizing the delay, which will be explained shortly. OpenExpress is prototyped in a Xilinx Vertex UltraScale 190, and the four 64GB DDR4 memories are used for the backend channel. Using 2.9 GHz Intel i5, building time for OpenExpress per each optimization phase take more than 7 hours. Even though it looks way longer than software building time, that's in a reasonable range for FPGA synthesis and implementation. We tune the operational frequencies from 50 MHz to the 250 MHz for the target FPGA. This figure shows a flow plan that illustrates each component of our Express. To have a high operating frequency, at the synthesis phase, we need to detect the worst-case logic routing delay as it decides the actual routing delay of our hardware model. We then split the load by placing the registers to increase the frequencies while minimizing FPGA negative slack. Let's consider FET as an example. We place multiple register slices to remove the input and output delays. So it looks simple, but this process cannot be done in just a single-shot synthesis. Specifically, we require checking the negative slack and perform this tuning for all logic as a gradual trial and error fashion. Even though register slice and route splits can help to increase the frequencies, still the long route among the multiple logic models exist. In the floor planning, we dedicate different model into the different part of grid cells by allocating hardware IP per FPGA P block and perform the place and route again. Like the synthesis optimization phase, this PNR is also performed in a gradual trial and error manners, which is a very time-consuming job. As a result of our frequency tuning, the performance is improved from the 20% to the 60% from the usual level observation. There are two insights that we can see from this analysis. The first, read exhibit more performance enhancement because of the dual simplex nature of the PCIe. Second, the larger size block processing is more beneficial thanks to the hardware automation. Let's see an example for this performance improvement. The NVMe device exposes PCI base address registers, called bar. When a user submits a request, the request includes PRP that indicate where data is. If the request size is smaller than or equal to 4 KB, it can be directly transferred from the host to the underlying storage media. That's everything. Otherwise, the target device requires go the location indicated by PRP2 and then fetch a set of PRP from the host. And this is actually not the data, but just a set of pointers. It then traverses all PRP entries and transfers each of them, which require high frequency to operate and transfer the data from the host to the storage side. For the evaluation, we use 10 I/O worker thread, as we observe that the power of a single thread is insufficient to extract the full bandwidth of OpenExpress. Note that the result that I'm going to show from now on is achieved with 8Q I/O depth, as it exhibits the best performance from the bandwidth angle. It's not a single I/O queue, so the latency could be longer. While we compare OpenExpress with a real fast NVMe device, in particular Optane SSD, we do not claim that it can be faster than any other future NVMe storage cards. Instead, we focus on demonstrating an FPGA-based prototype can be a research vehicle in storage system study. OpenExpress shows 2.8 GB seconds to the 7 GB per second bandwidth in this benchmark, the Microbenchmark test. Thanks to the hardware automation, the benchmark evaluation shows no difference between the random access pattern and the sequential access patterns in terms of bandwidth. The latency trend is also similar to each other's. And note that even with a higher Q-depth I/O processing to provide maximum bandwidth, the order latency is under a few hundred microseconds. For 4 KB size request, even there is no bandwidth differences between the reads and the writes. However, for larger size block processing, OpenExpresses exhibit much better read bandwidth than writes. And the question would be like, why are writes slower than the reads? So it's because of the dual simplex characteristic of PCI interface. The two processor request, we have to handle a doorbell update, NVMe command fetch, decode, and the PRP traverse first. Then we can see the location of the data and ready to transfer the data, which are all performed as inbound PCI packet processing. For the next request, we require doing the same thing. However, the request for the read and the data for the read are delivered from the device to the host through the outbound PCI path, so it can be overlapped. In other words, for the writes, all page rows are serialized. In contrast, the read data and NVMe page rows are served in parallel way. In addition to the microbenchmark, we also replace near real traces from the user level. Note that most SSDs cannot reach their best performance with a real workload execution due to different I/O behaviors compared to the microbenchmark, and different varying the request size and different operation commands, and the read-write are usually intermixed. For the read-intensive workload, the OpenExpress provide around 4.5 GB per second with a few hundred microseconds. For the write-intensive workload, it is offered as high as 2.1 GB per second, but all the latency of them is under 100 microseconds. For the bandwidth and the latency, OpenExpress shows 76% and 68% better and shorter latency than an Optane SSD. For read-intensive workload, it exhibits 111% better performance compared to Optane SSD. Note that, again, we do not claim OpenExpress prototype can be faster than any other future NVMe device technology. What we want to demonstrate is that the FPGA is yet much slower, as we all know, but the FPGA design and implementation for NVMe cores are not sitting on a critical path and can be used for system-level studies as a research paper. So let me conclude this talk by providing the related work and the download information. So there are a few third vendors to deal with the NVMe controller IP cores, which might be similar to us, but unfortunately, we cannot access them. I removed the actual name of the vendors from this figure. The main challenge from the academia, including me, is their high per month unitary prices. It's around $40,000. At least for me, I cannot access it. And for the prices of the single use, source code is around $100,000. So in this work, what we did is we provide OpenExpress, which will be freely downloadable for academic and non-commercial purposes. And OpenExpress include hardware automation IP cores such as HTRW, FET, CMT, and CTX. And we also provide the firmware for microblades to control non-performance critical administrator command management and device initialization, etc. And the open source, they also will include the Vivada project for the ultra-scale 190. So you can download such RTL and our IP cores from openexpress.camelot.org. Thanks for your listening.